Okay, you see, in our last class, I showed to you one of the most important consequences of hydrostatic equilibrium, and that is basically Virial theorem. This was Virial theorem, right? And we obtained it using both the hydrostatic equilibrium equation as well as we applied it for an ideal gas. So these two applied and we got the Virial theorem, right? And our basic expression was, you must remember, E internal or E thermal. So the expression was this is equal to minus half of E gravitational. So this was the expression. Now you must remember that while deriving this, we did not make any approximations or any assumptions. You must note this. We did not make any approximations other than assuming your E thermal or E internal is equal to E kinetic, right? And also it is important to note that this equation, this holds for any pressure at a radius, at a distance r, any temperature and any mr, as long as the star is in hydrostatic equilibrium and as long as we have ideal gas. Okay, so this is very important to remember. Now, an important consequence of this relation is the following. So I can write this, I have discussed, I think. Let me just recap for you. So I can write E total is equal to E internal plus E gravitation, and this gives me basically minus internal using the last equation, or half of E gravitation, which is less than 0. So basically we get the result that the total energy of a star is equal to half of its gravitational potential energy. And this has got very important consequences. So let us discuss the consequences. Now the first consequence 1. The first consequence is that, you see, gravitationally bound gas spheres must be hot. So gravitationally bound gas spheres must be hot to maintain hydrostatic equilibrium, and basically the heat provides the pressure required to balance gravity. The more compact such a sphere, the more strongly bound, and hence the hotter it must be. Now the second consequence is that a hot sphere of gas radiates, right? It doesn't just sit around. It will radiate into surrounding space which has lower temperature. Therefore, a star must lose energy from its surface. Now, this is very logical. However, note that the rate at which the energy is radiated from the surface is basically the luminosity. Rate of energy lost from surface is basically your luminosity L. Now in absence of internal energy source, this energy loss, basically luminosity, this energy loss must equal the decrease of the total energy of the star. That means L must be equal to minus d total dt, right? And this must be greater than 0 since your luminosity is positive by convention. Okay, now let me talk about the third important consequence. Well, you see, if I take the derivative of this relation, basically this one, E total is equal to minus, is equal to half of gravitation, then what I will get is that as a consequence of losing energy, I will get E gravitation is equal to minus 2L. I am just taking the time derivative and I am noting that L is equal to minus dEt total, right? So what does this mean? This means this, that is, this means star contracts and becomes more strongly bound. Okay. Also, we note that E internal, no, not derivative, we note this, you see, E internal, derivative, this is basically your luminosity and this is greater than 0, which I was talking about previously. So this means that here the first is the star contracts and becomes more strongly bound. However, this means that the star gets hotter, right? Now this is very unlike familiar objects which cool when they lose energy, and as a result of this two, we can say that a star has negative heat capacity. You see, half the energy liberated by contraction is used for heating the star, whereas half of the energy is radiated away. So, half of energy liberated by contraction is used for heating the star, and the other half of energy is radiated away or lost from surface. Okay, now there is another very interesting point, which is that in case the star, in the case that, suppose, another consequence, you can think that suppose a star is dominated by radiation pressure. Okay, then you see we will find that this E internal is equal to minus E gravitation, and therefore E total is equal to 0. What does this mean? So this means that a star dominated by radiation pressure, or more generally by the pressure of the relativistic particles, which are photons, right, is only marginally bound. So you see no energy, so marginally bound star. So no energy is required to expand or contract such a star, and even a very small perturbation would be enough to render it unstable and to trigger its collapse or complete dispersion. Okay, so these are the important things I would like to discuss with you. Oh, just a second. I think, I have made my point quite clear. Let me, before I finish, let me talk a little bit about the importance of this Virial theorem in the early stages of, in understanding the early stages of evolution. So let me first again write this down, this form. So E thermal or E internal is equal to minus half gravitation. So we would like to understand early stages of stellar evolution. Okay. You see, in the very beginning, when the star starts to contract, it releases gravitational energy, which is transformed. So a star starts to contract. Okay, so what happens is that it releases gravitational energy. Fine. Now this gravitational energy, this one is transformed to thermal energy, right? And star heats up. Okay. Now you see, as a result, the star reaches hydrostatic equilibrium when one half of released gravitational energy, that means one half of E gravitation, is stored as thermal energy. Right. Now you see what happens if more than one half of the gravitational energy were stored as thermal energy. Then the star would be too hot in the interior. And what will happen? You see, what will happen is that the pressure would then be too high, and the pressure forces would be larger than the gravitational forces. And as a result, the star would have to expand again. However, due to expansion and the consumption of the gravitational energy, the star would cool off until equilibrium is again reached. So you see that before the star can further contract, it has to lose some of its thermal energy by radiation at the surface. If no other energy source other than your gravitational energy is available, then what will happen is that the temperature would decrease. The star can then continue to collapse, heating up in the process. Remember that after each infinitesimal step of collapse, the star has to wait until it has radiated away half of its released gravitational energy before it can continue to contract. Okay, you see, with increasing gravitational energy release during contraction, that means with decreasing radius, this thermal energy has to increase in order to balance the increasing gravitational forces. And so the star continues to heat up while the radiative energy loss at the surface tries to cool it off. This is very interesting. Okay, so you see, we can understand all this stuff using just this simple one line over here. This one, you see, this Virial theorem. It's of great importance in stellar astrophysics. Okay.